Okay, so, thank you. So we're going to start a couple of lectures on nuclear magnetic resonance spectroscopy. So this is NMR. So we're looking at nuclear magnetic resonance, or NMR spectroscopy. And this is really one of the workhorse techniques in organic chemistry. We've looked at UV-Vis, which has value but somewhat limited, particularly today, with the emergence of more refined, in some ways more useful techniques, although UV-Vis does have some value. We looked at IR in some depth. And then NMR is probably by far the most important, certainly for organic chemists, of the spectroscopic techniques. While UV-Vis is very helpful in determining whether a compound has a pi system, what is the extent of that pi system, whether there are heteroatoms that are a part of the pi system. That's what UV-Vis sort of gives us. Not to mention the quantitative aspect of concentrations and so on. IR, on the other hand, is much more valuable for determining the presence or absence of certain functional groups. And that's actually pretty useful. One can imagine, for example, that if I'm doing a reaction in which I'm hydrolyzing a nitrile to make the corresponding carboxylic acid, and then my intent is to reduce the carboxylic acid down into, say, the aldehyde. Let's say that's my synthetic sequence, okay? The best technique for doing this is IR, right? So I could use IR to follow the progress of this reaction. Because in the starter material, I'll have the band at 2250 for the nitrile group. But as the reaction progresses, that band disappears to be replaced by a carbonyl band at 1710 and an OH band that's very broad, right? That starts about 3600 to about 2400. So I can see the disappearance of the cyano band and the emergence of the carbonyl and the OH for the carboxylic acid. And then if I was going to reduce this down to the aldehyde, well, the carbonyl stretch won't change, but the OH band will disappear, right? And in its place, I'll end up with the CH doublet at 2800. So by far, IR is very valuable for, probably the most valuable technique for determining the presence and absence of functional groups. And it's very common to use IR as a spectroscopic technique to determine the extent of a reaction, right? The progress of a reaction, particularly when the reaction involves FGI, functional group interconversion. So what we're going to look at today is NMR, which, as I mentioned, is one of perhaps maybe the workhorse technique in organic chemistry. And what I'll do in this lecture is to try to just introduce very briefly the physics of NMR. We won't go into any sort of great detail, it's not absolutely necessary. But just enough to have a working knowledge of how it operates. So we look at some very brief indication of the physics of NMR, and then we'll get into what does an NMR spectrum look like, what are the things that contribute to it, what can we glean from an NMR spectrum, and then we look at correlation tables and try to do some analyses of NMR spectrum. So I'm just going to close this door. Okay, so NMR, as we said, is nuclear magnetic resonance spectroscopy. And to make it very simple, the nuclei of certain atoms behave as if they were spinning magnets. And how do we know which atoms these are? Well, they would need to have either an odd atomic number or an odd mass number. So I'll say and or. So the nuclei that are magnetically active, right, that will give a response to the NMR phenomenon are those that either have an odd atomic number and or an odd mass number. So for example, protium, the smallest isotope, the lightest isotope of hydrogen, has an atomic number of 1 and a mass number of 1. Deuterium, because the atomic number is 1, right, is going to be magnetically active. So really, all 3 isotopes of hydrogen, protium, deuterium, and tritium, are magnetically active. Okay? Helium is atomic number 2. And in its normal form, helium-4, that is magnetically inactive. But helium-3 would give the NMR phenomenon. For carbon, carbon-12, right? Carbon is element number 6. So carbon-12 is not magnetically active because it has neither an odd atomic number nor an odd mass number. So carbon-12 is not magnetically active. However, carbon-13 is. Carbon-14, on the other hand, would not be. So of the atoms we have on the board, the ones that are not magnetically active are helium-4. And when I say helium, the atomic number is automatically 2. So helium-4, the 4 refers to the mass number, is not magnetically active. I can't get an NMR of helium-4. Carbon-12 is not magnetically active, nor is carbon-14. Okay? And I'll just do one more. Nitrogen is element number 7. Nitrogen-14, which is the common isotope. And really, all isotopes of nitrogen will be magnetically active because they'll have an odd atomic number. This requirement of having either an odd atomic number or an odd mass number, that is a quantum mechanical requirement. Okay? And that's all we say about it. All of the atoms that have odd atomic numbers or odd mass numbers are magnetically active, and I can get NMR spectra of them. We are mostly concerned with the NMR spectra of protium and carbon-13. And I will just say, in a sort of preemptive fashion, that we're fortunate that of the 3 isotopes of hydrogen, by far, the one that is most abundant is protium. So with proton NMR, we get really great sensitivity because H1 is by far the most abundant isotope. We are not so fortunate with carbon. Carbon-12 is by far the most abundant isotope of carbon. So carbon-13 is present in less than 1%, about 1%. And so the sensitivity of carbon-13 then is going to be somewhat sabotaged because it's roughly 1 in every 100 carbon atoms that will actually give you the NMR phenomenon. So there is an immediate problem with lack of sensitivity in carbon-13, and that problem does not appear in proton NMR spectrum. So often when we write this, we will say this is proton NMR, which we write like this, so it's proton NMR, right? And that indicates we're dealing with the protium, right? The smallest, the lightest isotope of hydrogen. Okay, so some nuclei behave as if they're magnetically active. And what exactly does that mean? Well, these nuclei will have dipoles. And the dipoles initially are all very random. Okay, so they're all very random. And so when you were to take the vectoral sum, on average, the vectoral sum is 0. Because if I have a sample that contains, lots of hydrogen atoms in it, then you take the vectoral sum of the magnetic dipoles, they cancel each other out. But what happens is, if I apply a magnetic field, and for the moment, let's say the intensity of the applied field is B naught. If I apply a magnetic field to these magnetically active nuclei, a sample of the magnetically active nuclei, what they do is they align themselves. In fact, what I'm going to do instead is I'm going to say, I'm going to apply B naught, but I'm going to have B naught operate in, let's say, this direction. So my field, B naught, operates in this direction. I'm going to apply the field this way. What I find is that the nuclei align themselves relative to the field. And they align themselves in what we call two different spin states. In one spin, they will be aligned parallel to the field. And in the other spin state, they are aligned anti-parallel to the field. So there's a parallel and there's an anti-parallel. So two separate spin states arise. Now ordinarily, in the absence of a field, the spin states are random. So there's no net dipole. When I apply the magnetic field acts as a frame of reference along which the spins of the nuclei align, either with the applied field or against the applied field. It turns out there's slightly more of them in the parallel state than there are in the anti-parallel state. That has consequences which we really will not get into. This is an introductory course. We're not going to get into much detail. But you can imagine, to some extent, that the applied field is like a river that has a strong current. And if you jump into the river and you swim with the current, right? You swim with the current, you expend less energy than if you were to swim against the current. And in much the same way, these two spin states, relative to the applied field, are really at two different energy values. There is the low energy parallel state, right? There's a low energy parallel state, and there's a higher energy anti-parallel state. So as a result of that, we create a delta E, which did not exist before we applied the field. If you remove the field, these all get randomized again, and there is no delta E. There's no energy difference. This delta E exists only in the presence of the applied field. Well, it turns out that this delta E is bridgeable by photons whose frequencies are found in the radio frequency band of the electromagnetic spectrum. So when we look at the EMS, the electromagnetic spectrum, so far we've looked at the ultraviolet visible band, right? That was our UV vis. We looked at the infrared band, and way down here, which is really wide, there's the radio frequency band. And it turns out that these delta E's are really small, and so the photons that can bridge them are very low energy photons. Because if you remember, in this direction, we have a frequency increasing, we have wave number increasing, we have energy increasing. And in this direction, we have wavelength increasing. So the very low frequency, low energy, right, photons in the radio frequency band have enough oomph to move the spin states, the nuclei, from a low energy spin state to a high energy spin state. So you can imagine that what happens when I apply photons of frequency nu p is that they cause a spin flip. So this one simply becomes, in the excited state, I would move this one so it goes here, and that disappears. Okay. So when my nucleus absorbs radio frequency of the correct frequency, the correct wavelength, then there's a spin flip, and we promote a proton from this low energy spin state to a high energy spin state. And we can record at what frequency that happens. Obviously, as with all promotions, it doesn't stay there, and eventually relaxes back down to the ground state. Okay, so I can measure then the frequency of the photon used to carry out the transition. Now, it turns out that if this was all there were to NMR, then NMR would be useless. Because if all I did is apply the field, and that creates a delta E, and I shine light at a certain frequency and we promote, all photons, all protons would have given the same delta E value, and therefore they all would show up with the same nu value, and there'd be no distinguishing one proton from the other. So how is it that they're distinguished? Why is NMR valuable? And the reason is, it turns out that the field that we actually apply, or B naught, is not really the field that a proton actually feels. Let me explain what that means. So, for example, let's imagine I have an H attached to a fluorine and an H attached to a silicon. So I'm looking at a silane versus, say, HF. So fluorine is the world's most electronegative element. So if I have an H attached to a fluorine, that fluorine is actively bleeding electron density from the H. And so the amount of electron density around this H is really very small. It's got a real paucity of electron density around that H, because most of it is being sucked away by the electronegative fluorine. Sorry, I've got something in my eye here. Most of it is being sucked away by the electronegative fluorine. On the other hand, silicon is an electropositive element. Electronegative draws electrons. Electropositive releases electrons in covalent bonds. So the silicon is actually dumping electron density onto the hydrogen, and so there's a robust amount of electron density around that H. So the intensity of the electron density around the H's differs, right, based upon the atom to which they're attached. And as we see later on, that's an inductive effect, and the other things that affect the amount of electron density. Why is that important? It's important because when I apply a B naught, so this is the applied field, I set my instrument to have a field of 300 megahertz or whatever. Turns out that what the nuclei feel is not this number. Because as I apply the field, the electrons around the nucleus are induced to generate their own magnetic field, which always acts in opposition to the applied field. So when I apply B naught, the electron density here orients itself in opposition of B naught. So I'm going to have, because there's a small amount of electrons here, I would have a relatively small opposing field. Okay? And I'm going to call this a B induced. That is the induced field caused by the applied field. But because there's a lot of electron density around this H, there's a much more robust response by these electrons to the applied field. And so the induced field here, my B induced, I'm going to call it B induced prime, is much larger because there are more electrons. And the electron density is always going to occur in opposition to the applied field. So the induced field is always in opposition to the applied field. So now, if I were to take the vectoral sum of B naught, right, the applied field, and B induced, the fields created by electron density in response to the applied field, I end up with what's called a B effective. And the B effective, I'm going to call this one B prime. The B effective is going to be defined as the B naught minus the B induced. And here that's the B naught minus the B induced prime. So what this means then is the effective field that these protons feel is larger than the effective field that these protons feel. Right? In other words, what's happening is these electrons better shield the nucleus against the perturbations, the effects of the applied field. So the more electron density I have around an H, the more I shield that H against the effects of the applied field. Because the more electron density I have, the more intense is the applied field, the more intense is the induced field in opposition to the applied field. So I get two different B effectives for these two different types of protons, depending upon the amount of electron density around them. That could be an inductive effect, a resonance effect, and so on. And what happens as a result is that the energy gaps are different. Because the size of delta E, the size of this delta E, doesn't so much depend upon B naught, does a little. It really is dependent upon B effective. And to the extent that B effective depends upon B naught, yes, they're related. But it's not just B naught, it also depends upon the induced field. So protons in different chemical environments that have different amounts of electron density around them will give me different B effectives. And for every B effective, there is a delta E. For every delta E, there is a photon of frequency nu p, right, that will bridge the gap. And so we can distinguish between the protons based upon the photon, right, frequency, which is dependent upon the delta E, which is dependent upon the B effective, which is dependent upon the induced field and the electron density around the H. This is why NMR is of value. Because protons in a molecule are very, very sensitive to their environments. And the amount of electron density around those protons changes very, very uniquely based upon those environments. So we can say that if I find a proton at a certain value, then those protons are highly shielded, right? If I find a proton at a certain value, then those protons are highly de-shielded. And there's a correlation between the frequency of the proton, where the proton is found, and the chemical environment of that proton. Okay? Well, we mentioned before that when we look at a spectrum in general, we are looking at, in most of the spectrum, we look at some sort of absorbance term against some energy term. So in UV vis, we literally looked at absorbance, right, against wave number. I'm sorry, against wavelength. So for UV vis, the energy proxy was wavelength. For IR, we had a transmission, and we looked at the wave number, right? Which was so we looked at these are IR bands. We looked at wave number as our energy proxy. So what's our energy proxy? What's our term for energy in NMR? And what we use for NMR is something called a delta value. And the delta value really is related to the frequency at which the proton under consideration appears. The frequency at which this appears was the frequency at which this one appears, relative to a standard. We'll talk about a standard in a second. So we define the delta value as the frequency of the proton under observation, the H in HF, the H in silane, for example, minus the frequency of a reference proton over the operating frequency of the instrument, 60 megahertz, 100 megahertz, 300 megahertz, times 1,000,000. And so what this does is it makes this a parts per million number. So the units of delta would be parts per million. So really, your delta value is a difference, right? It's a relative number. We look at the frequency at which our proton under consideration appears, and that's a consequence of the chemical environment of the proton, how shielded, right, or de-shielded it is. We look at that frequency relative to the frequency of a standard. We take that difference, we divide it by whatever the operating frequency of the machine is. We multiply that by 1,000,000 to get numbers that are parts per million. And so when I run the NMR of a typical compound, what you'll see is we run it from about 0, typically to about 12, and that's in ppms. So I'll have a delta value that runs from 0 to about 12 ppm. That's a classic range, the classic window, the spectral window for proton NMR. Okay? When we do carbon-13 NMR, that runs from about 0 to about 280, 260 or so. And yet, within this very small range, I capture the vast majority of protons that are found in organic compounds. I will point out, there are some peculiar cases where you find protons that are beyond 12. There are cases where you find protons that are below 0, right? But 99% of the protons found in run-of-the-mill organic compounds exist in that window. So let's talk a little bit about what the reference is. We will not dwell too much on it. And the reference that we use for most organic compounds is something called TMS, which is tetramethylcyanate. Right? So TMS. So that's silicon with 4 methyl groups. And as we mentioned earlier, silicon is a fairly electropositive element. And so what ends up happening is that we end up having a large amount of electron density around the H's in TMS. Why that's important is because in organic compounds, most of the H's are found attached to carbon. So if you look at the average organic compound, you're looking at an aldehyde of some sort or whatever, most of the H's are attached to carbon. There'll be some H's attached to heteroatoms, right? There'll be H's attached to heteroatoms, but the majority of H's found in organic compounds are attached to carbon. Carbon is not electronegative, so it neither pushes nor pulls electrons. And I say that with a full understanding that the hybridization state of the carbon impacts its electronegativity. So within a certain range, sp3 hybridized carbons are electron releasing, sp2 hybridized carbons are electron withdrawing, sp are even more withdrawing still. So there is a range going from sp3 to sp2 to sp where the electronegativity of the carbon changes. But in general, carbons are not particularly electronegative or electropositive. If I attach an H, if an H finds itself attached to an O or to an N or to a sulfur, well, those elements are electronegative, and they're going to bleed electrons from the H, and as a result, they will de-shield those electrons. So it means then that the average run-of-the-mill organic compounds has H's attached to atoms which either don't push a lot of electrons towards them or sucks away the electron density. So most H's in organic compounds find themselves in a region between about 0.9 to about 11-ish, 12-ish. So most H's find themselves here. And that's because those H's are not shielded. Those H's don't have something which is actively dumping electron density into them. So when we use TMS as our reference, we do that very deliberately because the silicon is dumping electron density towards the H. The silicon is shielding the H, causing an unusually high B induced, right? An unusually high B induced, causing therefore an unusually low B effective. And consequently, protons of that type, the shielded protons, appear here, very far up, what's called upfield. So we pick TMS as a reference because it shows up, those protons show up in a region where no other H's in organic compounds show up. And you want that. You want your reference to be clear of the things you're studying. You want your reference to be separate from the analytes. Okay? So TMS is used because those H's are found free and clear of H's in organic compounds. So we set the value of the frequency we set the delta value for H's in TMS at 0. And let me explain what that means, right? So if the proton in TMS is the reference proton, then nu H is equal to nu reference, which means that number is 0. And 0 over anything is 0. So we're going to set the delta value of the H's in TMS, whatever my reference is, at 0. It's not that the frequency is at 0 because delta is a difference, right? Delta is a difference. And if it's the frequency of the proton in TMS, and TMS is the reference, these numbers are the same. And therefore delta becomes 0. So we're going to set that at 0. It's free and clear of all the typical protons in organic compounds, so I can run the spectra with TMS in impunity. The other reasons we use TMS is because TMS is inert. It is inert and it is volatile. And really it is also soluble in a range of organic solvents. So I use TMS because it doesn't react with anything, so it doesn't react with my analyte, and that's important because if I'm isolating some really expensive compound, or running the spectrum and it costs $800 for a gram, I don't want to make it impure. I don't want it to react with my TMS as my reference. So it's inert. TMS is a very low boiling point. It's exceedingly volatile, so I can get rid of it very easily from my sample. It dissolves in a range of organic solvents, which we use to dissolve our organic compounds. And TMS, because there are 12 protons in one molecule, the signal is intense. So we get a really intense signal for it. And as we'll see, the signal is a singlet. It just gives you a single peak, and we'll talk about that in some more detail later. So you get one really intense signal. In the bad old days, and we still do it with some instruments, when you were preparing a sample, you would put your organic solvent, you'd put your analyte and a drop of TMS. Or sometimes you would buy the organic solvent from Fisher Aldrich or whatever. And the solvent would already come with TMS in it. And so the reference was built into the organic solvent. And you simply dissolve your analyte and run the spectrum. Okay, so we explained, so delta then is our energy proxy. We say that the region at low delta value, which corresponds to a low B effective, is the upfield region. This is where we find shielded protons, right? Because this is when the B induced is large, so the B effective is small. So shielded protons appear upfield, and it's weird because upfield has a low delta value. And then as we go down this way, this is referred to as the downfield region of the spectrum. This is where protons are deshielded. So protons that are bled of electron density tend to appear at high delta values. It is a little bit weird that downfield is a higher delta value. There's a reason behind that, because originally NMR, the unit was something called tau, and the numbers went the other way, and then realized tau is just not an appropriate unit, but we didn't change the labels because it already said. Okay, so we have a rough sense then of which nuclei are magnetically active. We don't know why, right? We're not going to get into that. That's a bit more physics than we need. So we can identify which nuclei are magnetically active, which ones will give an NMR phenomenon. We talked about applied fields. We talked about the randomization of the spins in the absence of an applied field. We talked about when the field is applied, it sets up two spin states. One that's parallel, that's of low energy. One that's anti-parallel, that's of high energy. The delta E's are incredibly small and are bridgeable by photons in the radio frequency band of the electromagnetic spectrum. That's really low energy. That the B effectives, which is actually what the nucleus actually feels, what the proton actually feels, is determined not only by the applied field, but also by the amount of electron density around the H. The more electron density around the H, the more those electrons act in opposition to the applied field, the larger the induced field, and therefore the smaller the B effective, right? Because B effective is the difference between the applied field and the induced field. Protons that have a large B effective, that are highly shielded, appear in the upfield region of the NMR spectrum. Protons that are bled of electron density for any number of reasons, they appear in the downfield region, which has a large delta value. Delta is defined as the difference between the frequency of the proton under consideration and the reference proton, which is TMS, over the operating frequency. By multiplying it by 1,000,000, we make these parts per million. That's the unit. And we talked briefly about some reasons why TMS is chosen as a solvent of, as the reference compound. Okay, so let's talk a little bit about what we look for in an NMR spectrum and what are the things that impact it. So when we look at an NMR spectrum, we look for four things, although I will mention all four for the purpose of this course, which is Introductory Organic. We will only highlight three. The fourth one is not of major use in intro-organic chemistry. For a graduate course or an upper level organic chemistry course, it would be of value. So again, I'm going to just say the spectral window is from 0 to about 12. This is downfield. And this is where the deshielded protons show up. And this is upfield, where the shielded protons show up. Right? That's where we get a lot of electron density on the proton. So what do we look for? What do we look for in an NMR spectrum? Well, we look for the delta value, which is also called the chemical shift. And let's explain what that means. Remember, we define the delta right, as the frequency of the proton we're looking at minus the frequency of the reference over the operating frequency of the instrument times 1,000,000. Well, what we're really asking is, what happened to the H that caused its frequency to shift away from that of the reference? Right? So the reference proton looks like this. There's an H attached to a carbon attached to silicon. And we're asking, what did we do to our H to cause it to become less shielded? Exactly what chemical environment is my H in that caused its frequency to shift from the reference value to something else? So the delta value measures the chemical shift. The shift, the change in delta value, the change in frequency, caused by a change in the chemical environment of the proton. Because clearly, if we move an H from attachment to a carbon attached to silicon to an H attached to a carbon attached to O, well, the impact of O on that H is very different from the impact of silicon on that H. If I just change this heteroatom, if I just change an atom, I make a significant change. I've changed the chemical environment, and the chemical environment will cause the H, the frequency, to shift. Here, the reference frequency is whatever that number is. If that's what I'm examining, that's going to be 0. But here, that's going to show up at a delta value of 3.5. So this is a delta of 0. This is a delta of about 3.5. That's a chemical shift, right? The frequency shifted because the chemical environment changed. So my delta value is also called a chemical shift. The shift in frequency caused by a change in the chemical environment of the proton. How shielded it is versus how deshielded it is. So I look for the chemical shift, or the delta value, because that tells me what kinds of groups are in proximity to that H and how many of them there are, right? So I can tell, for example, if I have an H on an O, that's very different from an H attached to a C attached to an O, because the inductive effect of this O is felt very strongly in direct attachment, but less so if it's further away. That's the electronegativity issue. Okay? But that value is very different from if I have 2 O's, because the inductive effect is even greater, and if I have 3 O's, the value is even different still. So I can tell, based upon the chemical shift, what heteroatoms and how many of them are in proximity to the hydrogen, and really how close they are. Direct attachment, maybe 1 position away, maybe 2 positions away. Okay? And I shared with you on Blackboard a correlation table. Right? And the correlation table shows the chemical shifts of the different protons in the compound. So I'm just going to walk you through a couple, and we're just going to highlight a few. So if you look at, so let's look on the right hand, on the left hand side of the correlation chart, and it says table something 0.1. Chemical shifts of hydrogens attached to various functional groups. Yeah, right? Yep. Look on the left, sort of middle, and go down. H attached to C attached to F, they show up at around 4.3. I'm just going to pick a middle number, but 4.3. And that means that the H attached to C attached to F, that fluorine is actively bleeding electrons from the carbon. The carbon responds inductively by bleeding electrons from the H. And the delta value here is let's pick 4.3. If I have H attached to C attached to chlorine, well, chlorine is less electronegative than fluorine. So it doesn't suck as much electrons. Maybe it'll do this. Which means by induction, I'm going to suck even less. And so Sounds weird. And so this H only shows up about 3.5. On the other hand, if I have C attached to bromine, well, bromine doesn't pull as much as a Cl does, and so I'll only have a smaller effect here from the bromine, and that effect is only at about, say, 2.8, 2.9, somewhere around 3-ish, right? So we can see that as the inductive effect of the halogen decreases, the pull on the electron density from the H, the deshielding of the H, decreases. So the delta value shifts lower and lower and lower, right? It's less and less and less deshielded. Interestingly enough, the electronegativities of Cl and O are almost exactly the same. And so O attached to C attached to H is also at 3.5, right? Just like the Cl, because the inductive effect is about the same. Okay? If you look, so if you look at a gem dichloro compound, so where I have 2 Cl's on the same carbon, well, the delta value for this now has gone from 3.5 over 5.8. Yeah, to about 5.8. So this number for the gem dichloro compound jumps to about 5.8. And that's because you now have you now have this effect, which is causing a greater bleed of electrons from the H. Okay? So the inductive effect on the H depends upon who is in proximity, how close in proximity, and how many of them I have. And that makes perfect sense. Okay? So the chemical shift is a tattletale as to what is the environment of protons are in. Okay? Now, I would make the point that the combination of which heteroatom, how many of them, and where they are, because there are multiple factors all operational simultaneously, it is possible for an H in one environment to have exactly the same chemical shift as an H in a different environment, because the confluence of factors work out in that way, right? And so that does make HNMR a bit more difficult, particularly because the spectral window is so narrow. 0 to 12 is actually very narrow, and so the likelihood of protons overlapping is actually quite significant. That's not a problem you see in C13, because the range is 250, and it's very unlikely for them to overlap, plus the tricks we use in C13. There are also tricks that we use in proton NMR to tease the spectrum out. Some of those are expensive. There are reagents we can add called shift reagents. And what you can also do is go to operating frequencies that are higher and higher and higher. So at a low operating frequency, let's say 60 megahertz, you may get something that looks like that, right? And that might look, to all intents and purposes, like one signal. But if you go from 60 megahertz to 600 megahertz, that might tease itself out into that. Okay? Which is why many Research One universities spend lots of money to buy instruments of higher and higher operating frequencies. And currently, it costs about $100,000 for every 100 hertz. So a 600 megahertz machine costs about $600,000. Okay, so yeah, let me add something else here. So the chemical shift is one of the things we look at, and I'm going to come back to this. 2, we look at the integral. We look at the signal multiplicity. And we look at So there are, which is also called the J value. So there are four things we typically look at in an NMR spectrum. And we will not, for the purpose of this course, spend a lot of time on the coupling constant. It's important, but not so important at an introductory level. We will spend more time looking at the delta value, the things that affect it, the integral, and the signal multiplicity. Before this lecture ends, I want to spend a little bit of time on chemical shift, and then we'll pick up there at the end of the next lecture. Well, I'll tell you what, we'll end this lecture here. So when we look at an NMR, we look at these four features, and in the next lecture, we will see what factors contribute to those features, and how those features allow us to interpret NMR and to determine the structure of a compound based upon the NMR spectrum.